All right, welcome to The Explainer. Today, we're demystifying something you probably use all the time but rarely think about: the incredibly complex, real-time machine learning architecture behind modern ride-hailing and delivery apps. We're talking platforms like Uber, Lyft, DoorDash, the whole shebang. We are going to break down the exact system design that makes these massive, two-sided marketplaces tick. Because, let's be real, we've all been there, right? You check your phone and the ride is, say, 15 bucks. Not bad. 10 minutes later, a sudden rainstorm hits or a concert lets out, and bam, the price is practically tripled to 40 bucks. Your first instinct is probably to just curse the app for arbitrary price gouging. But it's actually not that at all. What you are experiencing in that moment is this fascinating, highly responsive mathematical balancing act playing out right in front of you in real time. And honestly, what makes this balancing act truly mind-blowing is the sheer scale and speed of the architecture. We are talking about millions of requests coming in every single day across hundreds of cities. When you casually tap that button to request a ride, all this incredibly complex data gathering, the supply and demand forecasting, and the intricate pricing math, it all has to happen in the literal blink of an eye, specifically in under 200 milliseconds. No pressure, right? So the absolutely crucial point here is that the true goal of this massive system is actually not pure revenue maximization. It is marketplace equilibrium. The algorithm is basically acting as this master tightrope walker, constantly adjusting to keep riders and drivers perfectly balanced. Think about it. If prices are too low when demand is high, wait times just skyrocket and reliability tanks because there simply aren't enough drivers. But if prices are too high, no one requests a ride and drivers just sit there idle. Surge pricing literally exists to clear the market, attract that supply, and reduce your wait time.
Okay, so here's our game plan for today. 1. The two-sided marketplace. 2. The anatomy of a request. 3. Fueling the brain. 4. The twin models. And finally 5. Trade-offs and guardrails.
Kicking things off with Section 1, the two-sided marketplace, or as we call it, walking the tightrope. At the end of the day, the platform's ultimate success absolutely hinges on maximizing long-term marketplace health. And that means high reliability, making sure requests are actually fulfilled and those ETAs are spot on. It requires healthy conversion rates and fair, compliant pricing. The system literally has to clear the market by matching the supply of drivers to the demand of riders, all while simultaneously predicting highly accurate arrival times, because setting user expectations and powering the routing engine is basically the name of the game here. Moving to Section 2, the anatomy of a request, sub-200 millisecond magic. Let's trace exactly what happens under the hood.
Everything kicks off with your context, your specific geographic location, which the system usually maps out to a precise hexagonal grid called a geohex, and the exact millisecond you hit request.
Instantly, that single request triggers a check against the real-time state of the network. The system looks around and says, okay, how many drivers are currently active and available right now versus how many open requests already exist in this specific geohex at this very moment. But just knowing the current state isn't quite enough. The system needs to see where things are going. So, historical trip data, current weather feeds, active event schedules, and complex spatiotemporal features all flow into a forecasting module. This predicts the immediate future of supply and demand for your exact location. That forecast then feeds straight into the pricing module. This is where the system computes a surge multiplier. And remember, this is all subject to strict regulatory caps. The algorithm calculates the exact price adjustment needed to nudge the marketplace back toward that delicate equilibrium between available drivers and requesting riders.
Meanwhile, in parallel, a twin engine is running. This is the ETA and routing model. It's crunching map data, historical travel times, and real-time road conditions like traffic and congestion to predict both the time it'll take to pick you up and the total duration of the trip itself.
And finally, we reach the end of the pipeline. The dynamically generated price and that perfectly calibrated ETA are bundled together and sent right back to your screen. This is what powers the dispatch logic. And incredibly, this entire multi-step process has completed in less than 200 milliseconds. Pretty wild. All right, Section 3, fueling the brain. Let's look at what the algorithm actually sees. Now, what's really interesting here is how neatly this massive volume of inputs is categorized to make those rapid-fire decisions. First, you have spatial features, things like road density or specific points of interest to understand location patterns. Then temporal features, like time of day, day of the week, major holidays, to capture those predictable demand cycles. And crucially, you have real-time features. This is the immediate ratio of active drivers to open requests, which basically feeds the system its live beating heart equilibrium signal. And the thing is, we can't just look at these geohexes in a vacuum. As the source material points out, spatial spillover matters. Demand and supply in neighboring hexes absolutely affect your given hex. Think about it. A massive surge in demand in a neighboring downtown area directly tugs at the tightrope of your own quiet neighborhood's equilibrium. Why? Because available drivers will naturally relocate toward that surge, and riders might even walk across hex boundaries to avoid it. It's all connected. Which brings us to Section 4, the twin models, moving from simple baselines to deep learning. Back in the early days, these systems were pretty basic. They relied on simplistic historical baselines, just looking at average demand by hex and time, or using basic map distance heuristics for routing. Today, though, production systems use incredibly robust machine learning models, primarily gradient-boosted decision trees. Now, while massive spatial temporal neural networks do exist and capture super complex patterns, they are heavy, like incredibly hard to operate reliably at a citywide scale. So the industry trade-off is often sticking with gradient-boosted trees combined with excellent spatial temporal features, because they offer a highly reliable, interpretable standard for production. And this brilliantly highlights a really fascinating quirk in model design, especially when predicting ETAs. You see, the system doesn't actually aim for absolute perfect accuracy. I know, weird, right? It uses something called quantile or pinball loss instead of just mean absolute error. And the reason why is super clever. They have to intentionally control the bias direction. Think about it. If the model is slightly too pessimistic and says a ride will take 10 minutes when it takes 8, you might not book it. But if it's too optimistic and says 3 minutes when it actually takes 8, you get frustrated and probably cancel the trip altogether. The model is mathematically tuned to balance that exact behavioral tightrope. Let's wrap things up with Section 5, trade-offs and guardrails, and what we call the invisible data. One of the most fascinating challenges this system faces is a concept called censored demand. Okay, picture this. You open the app, you see a massive search price, or no available drivers, and you immediately close it. That right there is unmet demand. But because a trip never actually occurred, it's essentially invisible to standard training data. These are literally the ghosts of the marketplace. If the system doesn't mathematically correct for these missing data points, it creates a massive blind spot, causing the algorithm to chronically underforecast future demand. And look, because this system operates at such massive scale, failures are inevitable. So mitigations are baked right in. They use smoothing techniques to prevent prices from wildly flapping up and down second by second. If the complex machine learning models suddenly fail, the system falls back gracefully to historical data so it never blocks a user's request. When testing new algorithms, they use complex switchback or geographic experiments instead of basic A/B tests to handle marketplace interference. And importantly, they constantly run audits on pricing to ensure the algorithm operates neutrally and doesn't accidentally penalize certain neighborhoods based on skewed data. So, stepping back, it's this remarkably intricate dance of supply, demand, and predictive data, all happening flawlessly in milliseconds. But as these spatial temporal deep learning models continue to evolve and capture even more of our daily patterns, it leaves us with a vital question to ponder. How do we ensure the tightrope of fairness and AI pricing never snaps? Thank you so much for joining me for this explainer. I really hope it gave you a completely new perspective on what happens the next time you tap Request. Keep wondering and keep learning.